Hello, so in this lesson we're going to be talking about properties of definite integrals, and I've taken these properties of definite integrals from the textbook. They list them and they say we present these properties without proof. The proofs are straightforward. That's the only explanation the textbook gives, so I thought it would be wise just to spend some time going through these properties. I'm not going to be providing rigorous mathematical proofs, but just kind of intuitive visual ones. So let us begin. So here we have the definite integral of f of x with respect to x between b and a, and we know that corresponds to the area underneath the curve f of x between b and a. So what we're now going to do is we're going to consider if we add in another point between A and B. So let's say the point C. And this C could exist anywhere between A and B. Well, if I add in that point, what would the definite integral of f of x with respect to x between b and a equal if I had this extra point? Well, hopefully you can kind of anticipate what this is going to be. What we're going to do is we're going to say, well, the definite integral of f of x between c and a, so c and a is going to correspond to this area. So then I would just have to plus on the definite integral of f of x between b and c. So b and c would correspond to this area. So by plussing together these two areas, obviously it's going to be equal to what I started with. And this C could be located anywhere between A and B. As long as I'm plussing this region with this region, I'm going to be equal to this. And at this point, you're probably thinking, this is probably why the textbook didn't provide proofs, because that's pretty straightforward, isn't it? But it still helps to have a bit of a visual to go along with it. So let us put that as our first property, and the first really means nothing. I've just allocated them numbers, but no, don't read any importance to that number. Okay, so let's now go on to our next one, and again we're going to start with the definite integral of f of x with respect to x between b and a, which we know corresponds to the area underneath the curve f of x between b and a. What we're now going to consider is what would happen if I reduced my value of b. And as you can see, as my b becomes smaller, or as we could say, as it gets closer to a, as my b gets close to a, I have less area, so this is going to be a smaller value. So as my b gets closer to a, I get a smaller value. Well, what would happen if b equaled a? So we would come up here and we would say, well, b now equals a. As you saw there, I just changed it, and now both my terminals are the same. My upper limit and lower limit of integration are the same. So visually, you would say, well, what area is now underneath the curve? And because we have the same point, there is no area underneath the curve anymore. It's 0. So again, pretty straightforward stuff. That is what we're going to call our second property. Okay, let's now move on to our next one, and we're again going to start with the definite integral of f of x with respect to x between b and a. Now, according to our fundamental theorem of calculus, we know how to solve this. The first thing that we do is we take the antiderivative and sub in our upper limit, and we know that's going to be all the area all the way up to b. And let's just give this a value. Let's just say this is 10. The next thing that we do is we take our antiderivative again and we sub in our lower limit, so a this time. And that corresponds to all the area all the way up to a. So the green area right here. And let's give this a value as well. Let's say that this is 6. Now, according to our fundamental theorem of calculus, we subtract these from each other, and by doing that, the green area goes away, so I'm just left with the area between A and B, and that's what we want. And in this example, that would be 4, because 10 minus 6 is 4. Perfect. What we're now going to do is just simply copy everything we've done here and move it over to the right. So we've simply just copied it over, and hopefully you would agree with me that these two statements, therefore, are equal to each other because they're identical. Because they're identical, they're equal, obviously. Okay, what we're going to do now is I'm going to switch my terminals. I'm going to switch them. Ready? I'm going to switch them. There they go right there. Perfect. I've switched my terminals. What effect is that going to have? Well, that means I'm going to switch them right here as well. They're going to switch there. And if I switch those, these are going to switch as well. So now I'm going to get 6 minus 10 as opposed to 10 minus 6. And 6 minus 10 is going to be negative 4. So now let's appreciate the fact that when we switched the terminals, our answer became negative. Our answer became negative. So that means when we switch the terminals, we have to put a negative in front. So this would equal negative when we switch the terminals right there. So let's now write that out again. So what this means is that if we have this, but then we switch the terminals, it's going to be equal to it, but just negative. Now, where does this become important, or where can we use this fact? Well, in our last lesson, we saw signed area, and we saw that when we have area above the x-axis, it is positive, but when we have area below the x-axis, it is negative. And we said, well, if you want to find the total area, what you have to do is you would say, well, the total area is going to be equal to 1 to 0. So my limits here are 1 to 0. And because this area right here is going to be negative, what I'm going to have to do is actually put a minus here, or a negative here, so that when I do find it, the two negatives cancel out and I get a positive. So I have to actually put a minus here, and that's a common mistake people make. They think, well, total area, you plus it, and they don't consider the fact that the area underneath the x-axis is going to be negative already. So, but knowing this property right here, let's copy this line down, and let's say, well, if we swapped the terminals here, if we swapped the terminals like that, I could make this positive, because now what I've done by swapping the terminals is I've made this area underneath the graph positive, because I swapped the terminals. So think about that for a second. It will probably might take a few seconds to click over, but like, oh yeah, that makes sense. Nothing too tricky there at all. All right, let's now leave that for the third property and move on to our fourth one. I really like this fourth one. It's finding the integral of a constant. So here we're being asked to find the definite integral of 6 with respect to x between 9 and 4. Well, what exactly is that asking of us? Well, let's first consider what 6 would be. 6 here would just be f of x is equal to 6, which is just y is equal to 6. So it's just cutting there at 6 right there. And then my upper and lower terminals here are 9 and 4, so let's draw them in as well. Now we know that definite integral is all about area, and this right here is a rectangle. So what if we just found the area of the rectangle? We know we're just going to find the area of the rectangle. We know that the height is going to be 6 because, you know, we've got f of x is equal to 6, so it's just going to be 6. What is the width of it going to be? Well, it's just going to be 9 minus 4, which is 5. So when you are performing a definite integration of a constant, all you do is you take that constant, then you subtract the terminals from each other to find the width of the rectangle, and just like that, so 9 minus 4 is 5, so 6 times 5 is 30. So the area here would be 30, and that would be the answer to that definite integral. So as you can see there, pretty simple, intuitive property, but it really helps having that visual. So that's what you do when you're finding the integral of a constant. And we could just write this like this. So instead of using numbers, I've just swapped them for letters, and that's what we like to do when we're writing down what properties are. And then what we could do finally is, this is just the final proof the textbook provides. So I just want to give it here, the final property in the final form. So all it says is that if we're finding the definite integral of f of x plus k between b and a, well, to answer that, what you would do is just take the definite integral of f of x, so treat that, and then plus onto that the height times width of the rectangle. So you're just treating it separately. So all I've done is taken that over there. So I've just added that a little bit there because that's how the textbook presents it, and it's how your booklet presents it as well. So just realizing that. Okay, so let's leave that there and let's move on to our fifth one. So this one doesn't have a nice visual, but we'll still go through it. If I was asked to find the definite integral of 4x squared with respect to x between 1 and 0, we know how we would do this. What you would first do is you would take the f of x squared and you would anti-differentiate it. So you'd plus 1 to the power, then divide by it. Then you'd put brackets on it with the terminals, and then you'd sub the terminals in, and you would find out that your answer is going to be 4 on 3. We know how to do that. Well, let's now copy this down. We can actually approach this from a different way. Here we have 4 times x squared. So we have a constant times something. What we can actually do is just take that constant out. And now we can just anti-differentiate what's in the inside here. So it's x squared, and I'm going to plus 1 to the power, then divide by that new power, and then don't forget to write my terminals there. And now I'm just going to bring my 4 across. So I'm going 4 times whatever this is going to be. Well, if I was to sub 1 into this, I'm just going to get 1/3, and this 0 is just going to go away. So what I'm going to be left with after all of that is 4 times 1/3, which is 4 over 3, which is the same as what we got up there. So what this is proving is that I can take out a constant that is being multiplied to a function. And this is how we will write that proof. So whenever you have a constant multiplied by a function, you can actually just take that constant out. And then it just makes it easier to anti-differentiate what's in there. And that's just makes your life a little bit easier. Okay, that is our fifth property. And now our sixth one, I don't have any visuals for it, but I think we've already seen it plenty of times before, so I don't think I need to. If we're finding the definite integral of f of x plus or minus g of x with respect to x between b and a, we can simply just break that up into two parts. We can do this, then we can do this. We've seen this before, and yeah, so nothing too tricky there. We can just break it up into those parts there. Okay, so with all that being said, let's now see these properties in action. So we've only got 3 questions here that we need to work through, so we will be able to do this rather quickly. So let us begin. So let's come over here, and we are told that given that the definite integral of f of x with respect to x between 3 and 1 is equal to 5, evaluate the following. So the first one we have to evaluate is this. And as you can see, I have a constant being multiplied by a function. So what I'm going to do is just take that constant out. So I'm going to get 3, then this, then this, then this, then that, dx. And I know that this right here, the definite integral of f of x with respect to x between 3 and 1, I already know that's 5. So this right here is 5. So it's just going to be 3 times 5. So my answer is going to be 15. How easy is that? Let us highlight that answer. Let us now move on to the next one. Here we have the definite integral of f of x plus 3 with respect to x between 3 and 1. So as you can see here, I have a constant, and we know what we're going to do with that. The first step I would actually do is write it out like this. I would say I have 3, 1, f of x, d of x, plus this, 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 and this. So I'm using that last property that we saw, that I can break things up like that. Having done that now, I have this, which I know is equal to 5, so I can put a 5 here, and I'm going to plus together what this is. Now, because it's a constant, I know it's just a rectangle, it's just the area of a rectangle, so the height is going to be 3, and then I just have to subtract my terminals, so it's going to be 3 minus 1, so that's going to end up being 5 plus 3. 3 minus 1 is 2, so it's going to be 5 plus 6. My answer is going to be 11. Let's just scroll down a little bit. It's going to be 11. So let's highlight that. Perfect. Let's now move on to our very last one, and then we're all done for this lesson. So as you can see here, what makes this different to this? Well, here I have 3, 1, and here I have 1, 3. So my terminals have switched. So that means that this is going to be negative. So we've seen this before. So this right here is going to be equal to negative. That's an ugly equal sign. Let me try that again, shall we? So this is going to be equal to negative of this one right here when my integrals are normal. That f of when my terminals are normal, or this way up. And we know what this is equal to. This is equal to 5. So it's just going to be minus 5. And that would be my answer. So when you swap the terminals, you just get a negative answer. And just like that, we have finished this lesson. Hopefully all these properties have been made sense and everything makes sense to you. If you have any queries or questions, make sure you reach out. See you in the next lesson.